In this part of the Neurocomputers and Deep Learning course related to recurrent neural networks, you will learn what is energy function and how to examine the stability of recurrent neural networks using Lyapunov theorem and also using Cohen-Grossberg theorem. An equilibrium state X star of an autonomous nonlinear dynamical system is called stable. X0 minus X star norm is less than Xt minus X star norm is less than epsilon for all t greater than 0. That means that by choosing the initial state close enough to the X star, then we guarantee that the state at any time is in the epsilon neighborhood of the X star. If X star is a stable equilibrium point, it means that any trajectory described by the state vector xt of the system can be made to stay within a small neighborhood of the equilibrium state X star by choosing an initial state x0 close enough to X star. An equilibrium point X star is said to be asymptotically stable if it is also convergent, where convergence requires the existence of positive delta such that x0 minus X star norm less than delta implies that limit as t goes to infinity xt is X star. This is the definition for asymptotically stable equilibrium point. If the equilibrium point is convergent, the trajectory can be made approaching to X star as t goes to infinity by choosing again an initial state x0 close enough to X star. Notice that asymptotically stable states correspond to attractors of the system. For an autonomous nonlinear dynamic system, the asymptotic stability of an equilibrium X star can be decided by the existence of energy functions, which are also called Lyapunov functions. A continuous function Lx, which is a scalar function on xt element of Rn, with a continuous time derivative, L prime x is 0 for x equal to X star. If this condition is in the form instead of less than, if we have less equal to 0, in that case the Lyapunov function is called semi-definite. The stability of an equilibrium point can be decided by using the following theorem. The equilibrium state X star is stable if there exists a semi-definite Lyapunov function in a small neighborhood of X star, or if we use asymptotically stable instead of stable, in that case it will be definite Lyapunov function. The use of Lyapunov functions makes it possible to decide the stability of equilibrium points without solving the state space equation of the system. Unfortunately, there is not a formal way to find a Lyapunov function. Mostly it is determined in a trial and error fashion. If we are able to find a Lyapunov function, then we state the stability of the system. However, inability to find a Lyapunov function does not imply the instability of the system. Often convergence of neural networks is guaranteed by an introduction of an energy function, Lyapunov function, together with the network SR. In fact, the Lyapunov functions are non-increasing along trajectories. Therefore, the dynamics of the network can be visualized in terms of some multidimensional energy landscapes as given previously. The attractors of the dynamic system are the local minima of the energy function surrounded with valleys corresponding to the basin attraction. So here, if we consider the energy surface, here we have local minima and the attractors are corresponding to these local minima. The convergence of a network to an attractor of the activation dynamics may be viewed as a retrieval process in which the fixed point is interpreted as the output of the neural network. As an example, consider following network dynamics. The time derivative of the output of the ith neuron at time t is equal to the output of neuron I at time t minus plus fi, the summation j from 1 to n connection weight from the j neuron to I multiplied by the output of the j neuron plus the threshold of the ith neuron. Assume that the weight matrix W is fixed and the network is specified through theta at the initial state x0. Both theta and x0 are ways of introducing an input pattern into the network, although they play distinct dynamical roles. This is the equation describing the dynamic of the recurrent network. We then distinguish two modes of operation depending on whether network has fixed x0 and input is applied as theta equal to u, or network has fixed theta and x0, the initial state set to input, is chosen. In the first case, network has fixed initial state and input is applied as theta equal to u. The vector u acts as input and the initial state set to some constant vector for all inputs. In general, the value of the attractors vary smoothly as the vector u is varied. Hence, the network provides a continuous mapping between the input and the output spaces. Although we are starting with the same initial state at the end, for different u values, different theta values, the network may converge to different final states. The same initial value x0 may result in different fixed points as final value for different u. In the second case, the network has fixed theta and x0 set to u is chosen. In this case, the input pattern is presented to the network through the initial state x0 while having fixed theta. The attractors of the dynamics may be used to represent items in a memory, while the initial states are the stimulus to remember the stored memory items. The initial states that contain incomplete or erroneous information may be considered as queries to the memory. The network then converts to the complete memory items that best fits the stimulus. So for each region, we have a fixed state, and if we start different initial states around x star in the basin of attraction, these fixed states will converge to the same x star. However, if we start with a different x0 belonging to some another basin attraction, then it may converge to a different fixed point. Different x0 may converge to different fixed values, although u is the same. Cohen-Grossberg theorem is useful in deciding stability of certain class of neural networks. The theorem is saying that given a neural network with n processing elements having bounded output signal FI/AI and transfer function of the form, the change in the activation of the ith neuron is equal to alpha I at AI and then in parentheses beta AI minus summation j from 1 up to n wji fj aj I from 1 to n. So this is defining the dynamic of the network. Satisfying constraints symmetry wji is equal to wij inj from 1 to n. This is saying that the connections are symmetric. Non-negativity saying that alpha here is greater than 0 for each I from 1 to n. The last condition, monotonicity, is saying that the derivative of function fj at point A, that is, derivative of the function fj at point A with respect to A, is greater equal to 0. So this is saying that the output function f is a monotonically increasing function. If these conditions are satisfied, then the network will converge to some stable point, and there will be at most a countable number of such stable points. So the given dynamic with the given conditions is guaranteeing the stability of the network. Furthermore, the function E, which is equal to 1 over 2 double summation I from 1 to n and j from 1 to n wji fi at point ai and fj at point aj. This is the value of the output function at ai and the value of the output function at I. This is the connection weight between these two neurons minus summation I from 1 to n integral from 0 to ai beta I at s f prime s ds is an energy function of the system. That is, E is bounded and has negative time derivative on every possible trajectory that the network state can follow. In the proof, due to condition 1, W is symmetric, the time derivative of the energy function can be written as dE dt is equal to minus summation I from 1 to n alpha I ai f prime I at ai and here in parentheses beta I at ai minus summation j from 1 to n wji fj at aj. And here there is a square. And it has negative value for a different than a star. This is the fixed point whenever conditions 2 and 3 are satisfied. Here, notice that if condition 1 is satisfied, that is, if the connection weights are symmetric, then the time derivative of the energy function can be reorganized in this way. Here we have a square, and the first derivative of the function is shown to be always increasing. It was a monotonic function. And also the condition 2 was saying that alpha is always greater than 0. So this part is positive, this square is positive because we have minus here. The time derivative of the energy is negative. And furthermore, because it is bounded, then it is guaranteed that it will converge to a fixed point as energy is changing. Since dE dt is less than 0 for ai different than ai star, the global system is therefore asymptotically stable. So this is showing that this given energy function is a Lyapunov function.